Hello, everyone. Thanks for coming. My name is MG Durante, and I'm here today to start this ReStructure 2.0 webinar series. So let's start. When I thought about this webinar series, the first thing that I was thinking was, what will be the first question that people can ask? The first question was, what is ReStructure 2.0? ReStructure 2.0 is a research project that is based at the Department of Civil Engineering of the University of Calabria in Italy. It was funded by the European Commission through the Marie Sklodowska-Curie Action or Integration Panel. That is a specific call that is voted for people that were working abroad outside Europe for a while and wanted to go back to Europe. And I am the PI of this project. Why I decided to start this ReStructure 2.0 webinar series. The main idea is to create an active network in which discuss about topics from the broader area of geotechnical earthquake engineering. And then since these webinars are open to everyone that is interested, not only academic, but also practitioners and everyone that is interested to the topic, I was thinking also to disseminate the research. The frequency of these webinars will be about one every month. And of course, we will have summer breaks and stuff like that. And this will be for the whole extension of the project that is the project is a two years long project. And where we'll take the webinars. For now, the first few webinars will be online only. But soon we're planning to have the webinar directly on campus at UNICAL, but the online connection will always be available for people that will be interested in joining all the following webinars. Who will be presenting? As I was mentioning, the topics will be on the broader area of geotechnical earthquake engineering. So worldwide experts will be involved in this, are involved in this project. Here you can see some of the confirmed speakers that are from the United States, from Italy, from Greece, Germany, and the order that you can see here is just the chronological order, and these are just the ones that are already confirmed their availability. How to be informed? As you find also on the subscription form, there is the option to subscribe to the newsletter from the official website. But also you can follow the social media pages. We have our Facebook, Twitter, and Instagram accounts. And every time we are uploading and all the information, all the events on these media. And why ReStructure 2.0? What is this project? I'm giving just a little bit of background for people that don't know me, just to give you the idea and to understand what's behind the project. As I was mentioning, this project was thought about for combining my expertise that I developed during my US period. In the US, I spent a total of more than 4 years. And the first 2 years, I was appointed as a postdoctoral scholar at UCLA, University of California, Los Angeles, working with Scott Brandenberg and Jonathan Stewart. And we started working on seismic pressure using a soil structure interaction principle. The soil structure interaction is my background. My PhD was on that. But during this period, I was working on different problems, retaining structure. The main outcomes of this period here at UCLA are two different solutions that we developed. The first one was a solution to analyze the complete frequency dependent solution. So it's a very complex analytical solution that is analyzing the response of a retaining structure with different boundary conditions and under dynamic input. And of course, and this will be later the focus of the presentation. So the actual webinar, the technical part, will focus on this. The other thing that I did during my period at UCLA was developing also a simplified solution, more easy to use, very easy to use compared to the complex solution. And this solution has been then included in the current FEMA guidelines. It means that basically it will become soon national code in the US. And Professor Brandenberg, Professor Stewart, and I are the three authors of this chapter. And just as a bit of spoiler alert, one of the next presentation will be focused on this new methodology, the simplified solution. Following the 2 years at UCLA, I moved to University of Texas at Austin, working as a postdoctoral scholar with Professor Ellen Rajeh. During this period, I was able to run APC, high performance computing analysis at TAC, because I was working in this big project, NSF funded project, Design Safe, where we are taking advantage of the Texas Advanced Computing Center that is hosting the fastest academic supercomputer. And then during this period, we also explored the possibility to use machine learning in geotechnical earthquake engineering problems. And during this period with Professor Rajeh, we studied and we applied these new techniques to a case study of extended lateral spreading, followed by the 2011 Christchurch event. So combining these two period of my life and also the expertise that I was able to develop in this period, I talk about ReStructure 2.0. This project is in fact is a novel physics-based methodology for the seismic analysis of retaining structure, leveraging machine learning techniques. So basically, I was able to combine all the best that I had, what I was able to learn in the US. So this is just a little bit of background of the project, and now we'll go directly into the actual presentation, so the technical part. As I was mentioning, in this presentation, we will focus on the response on the complex low frequency domain solution for retaining structure. Because why I'm talking about new soil structure interaction frontiers? Because until now, we had a different approach to this type of structure. We'll see that during this presentation. Before starting, there are a few people that I want to acknowledge. First of all, Professor Brandenberg and Professor Stewart from UCLA, and because I worked with them in my period at UCLA, and also Professor Mikulonakis, because we published all together this solution that I'm presenting. Professor Ellen Rajeh from the University of Texas at Austin, and Professor Roberto Cairo, that is the project supervisor here at UNICA. So we are starting this new chapter together. And also, I would like to acknowledge the funding agency, in particular the European Commission, through the Marie Sklodowska-Curie actions. Here there is the outline of this presentation. So we'll start with some mechanisms for wall-soil interaction. We'll check then some current practice in Europe, and also with some notes on what's going on also in the US and what's the recent research. I'll show then the actual analytical procedure that we are proposing, this new analytical solution, and showing some centrifugal test layout that we use for the validation of the model, because of course we had a big validation phase for this model. I will show you some resources available in the cloud for everyone, and what is the direction of future research with this project, and then we draw some conclusions. Let's start with the mechanism for wall-soil interaction. Before starting, I would like just to have few useful definition. Most of you are always familiar with all of these, but just to if there are people that are not familiar, we will talk about the main motion frequency, and we will use that to define the wavelength of the soil. That is defined as the ratio between the shear wave velocity and the frequency of the motion. We will refer to a free field motion, that is the motion recorded in the free field condition, so not influenced by the foundation. And we will use a foundation input motion, that is the motion that accounts for the complexity of the incident wave field and its interaction with the SIF foundation system. So it's what we are going to apply to the foundation. As we all know, the interaction mechanism can be studied. We can have two different approaches that we can use for study this problem. The first one is the continuum model or direct model, is the direct method. that consists basically in the analysis of the whole model, all the elements, the interaction, the interface element, the soil, and the structure. And we can use in this type of model all the level of difficulties that we prefer. We can use soil, elastic or inelastic soil, and the same we can do for the structure and for all the interface element. Another method that we can use to analyze this model is the substructural approach, that basically divide the problem into two different parts, and we analyze first what's happening at the foundation level, and then we apply springs and dashpot. We apply the motion through spring and dashpot to the structure and see what's the response. Of course, another simplification that we do is like to divide basically the problem into different components, to consider that we can have a kinematic response, that is the so-called kinematic soil structure interaction. When we consider just the foundation input motion, we don't consider the inertial forces, and the pressures are coming just from the difference between the wall and soil movement. And then we have the inertial soil structure interaction that basically accounts for the response, for the effect of the structure and its inertia on the response of the whole system. Of course, in this way, we are facing a simplification because there is a mutual interaction between these two components, but this is just a simplification that we're using. What are the important points? So that basically we know that both kinematic and inertial effects give rise to seismic earth pressures, and then both produce pressure at a result of relative moment between movement and soil. So there is always this component that we find. At this point, what's the current practice here? Something that is really common is to use the Mononobio-Cabe procedure. The basis, this is the basis in the method is at the base. It was introduced around the 24, 29, and it's still the method that is used with some modification in Europe in the Eurocode. So the reference code here is in Europe is the Eurocode 8. The difference is that in the US, as I was mentioning before in the initial introduction part, there are new guidelines that are not recommending Mononobio-Cabe anymore, but this new approach that is using soil structure interaction principles. We'll check then some results of recent research to check how this method, this Mononobio-Cabe procedure is performing with reference to some centrifuge tests and dynamic soil structure interaction analysis. Let's say just a few more words about the Mononobio-Cabe approach, how it works. The idea is that it starts considering the static earth pressure. So it can be active or at rest condition, and consider and compute the PA, so the resultant. And then it performs a limit equilibrium analysis using a seismic coefficient, KH, that is directly proportional to PGA, so to the peak ground acceleration. And then sums this increment of pressure to the static condition. What is the key? The key is that the horizontal acceleration must cause seismic earth pressure. So this is the key point here. This is a sketch. This is a classical figure that shows how the active earth pressure coefficient Ka is the seismic coefficient is changing with respect to the horizontal seismic coefficient. And you can see that the main thing that I want to outline here is that always, of course, depending on the combination of soil properties and input motion, there is an applicable limit for which we consider that basically we reach the limit condition, sorry, and it's what we consider like infinite seismic earth pressure increment. So we say that according to this method, we say that horizontal acceleration must cause seismic earth pressure. But is it true? If we try to see the problem, thinking about the soil structure interaction principles that we all know, we are used to when studying the structural response, for example, or pile responses, we can think about two different conditions. The first one we can consider when we have a low frequency motion. In case we have a low frequency motion, what we have, the result is a long wavelength. It means that basically, if we compare the response, so this displacement that we record at surface, if we have a long frequency motion, we see that the displacement that we have, the foundation input motion, the displacement that we have, that we are applying at foundation input motion is almost the same of the one that we have in free field condition. This is because there is not a big variation of displacement along this line until the depth of the foundation. So in this case, if we don't have a significant variation between the foundation input motion and the ground motion and the free field motion, and so we don't have a rotation, we don't even have a rotation of the foundation, we have negligible wall pressure. What is happening when we have a high frequency motion? If we have a high frequency motion, it means that we have short wavelengths. This is the extreme. This is the case when you have the minimum in correspondence to the base of the foundation. In this case, if you have short wavelength, it means that the difference between the response that you have here, up here at surface, and the one that you have at the foundation level is significant. So you will have a difference between the foundation input motion and the free field motion, with a consequent rotation also of the whole structure, and you will this will create large wall pressure. This way, we can see that horizontal stresses have no fundamental association with PGA. Another way of thinking about it is like when if you have low frequency motion, but the foundation is moving together with the soil, so there is no actual difference in the interaction between the two models. If they are not moving, if there is high frequency, there is high chance of having opposition of phase, so there will be more pressure at the interface between the two elements. If we are now checking some centrifuge tests that were done by Alatik and Sitar in 2009, the reference that we are using is the 2010, that is the journal publication for this study. They considered basically these U-shaped walls that were rigid or inflexible, and this is all the configuration. We have, of course, all the information are available for this test that they run. What they did, basically, they were running all these tests, and they checked using different input motion, of course, the different intensity. And once they compared the results, the experimental results, with the Mononobio-Kabe prediction, they saw that the predictions were that Mononobio-Kabe was always overestimating. Mononobio-Kabe is represented by the black continuous line, and while the gray line is the Mononobio-Kabe with the 65% that is considering 65% of PGA. It's also called this procedure is something that also suggested Sidde-Whitman with this reduction of the PGA, because they observed that using the full PGA was not matching well the recording. So in this case, we can see that Mononobio-Kabe is underestimating, is basically overestimating, sorry, the test, the laboratory test. So what they saw also checking the seismic coefficient, so the increment versus the PGA, they observed that for PGAs less than 0.4, there was no actual increasing of, there was not an increasing of the total response, so there was not sigma p. And then they observed this linear increasing. So they recommended no seismic earth pressure for PGA less than 0.5, and they found that in the other case, the Mononobio-Kabe was overestimating. Other analyses were here presented some more analysis about the dynamics of structural interaction, and these are the tests that were done by Ostadan in 2005. The difference with this set of data is that basically they are considering rigid walls, so there is no flexible walls. There is the fixed base condition, so there is a strong site response due to the resonant condition due to the fixed base that we have. This is for Ostadan 2005, but there are similar results also by Wood and Bellezza de Yunan. This is something that is very interesting, because when they ran these tests and they were comparing their results with the Mononobio Cabe, they found that the Mononobio Cabe predictions were way lower than the measured results. So in this case, Mononobio Cabe was underestimating the response. So basically, we have two sets of data. In one, we had an overestimation of the Mononobio Cabe procedure. In the other one, we have an underestimation. So all these, we can see that centrifuge tests, so the centrifuge tests tends to support pressure lower than Mononobio Cabe, while when you have strong resonant condition, there is like an underestimation. So this is the reason why there is some confusion about this method, and this is something that was ringing the bell for us, thinking that maybe there is something that was missing, and there is something that was not related to PGA but to frequency content. And so about the different response. So what is our proposed procedure? The analytical procedure, the scheme of the analytical procedure that we use is represented here. Basically, we are considering a Winckler model, and we are assuming the main hypothesis of this model is that wall is represented by an Eulero-Bernoulli beam with constant flexural stiffness that is constrained by elastic springs at the top and the bottom of the wall. Then we are assuming that the wall shape function are approximated, assuming Hermite cubic polynomial shapes. Sorry. And then we consider that the shear wave velocity profile is propagating vertically in an homogeneous soil deposit, assuming that the function of depth is the same that one proposed by Rovitis et al. Here is the shape of the variation with the depth. And another important hypothesis is that the depth variation of the Winckler stiffness has the same form as the soil deposit, so follows the same FZ function. This is, I promise that this is the only, even though we are talking about an analytical procedure, this is the only equation that I'm showing. And I'm showing this equation because I want to underline that in one of the main actor of this method is the difference, is this UG minus U term, that is basically the difference between the wall and the free field displacement. So in our model, it's the main actor. And this equation, for this equation, it is not possible to have a closed form solution. So we use the numerical approximation. All the details, all the equations and everything are presented in the Brandenburg et al. 2020 paper. Another thing that I want to show you is what we use for this KYH, that is basically is including the soil response. So how we are treating the soil. For this term, we are considering that we are considering the KYH0 because we are considering an homogeneous soil. So this is the value that we have at the bottom of the deposit, and then we are considering 3 scaling factors. One that is related to the frequency, one related to the length. And for length here, we are meaning the distance between two walls, because the method is also can take into account the presence of the wall that is close enough to influence the soil responses, so we don't have an actual free field response. And then we have this scaling factor that is related to the flexibility of the wall. How we compute this KYH0? Of course, this solution is for homogeneous soil, but the homogeneous case is also can be also used. And in that case, we are using the formulation by Kuklinas et al. 2012. While for inhomogeneous soil, we are using this equation for KYH0, that is the value that we use at the base, the reference value at the base of the wall, and then the distribution is following this FZ, that is the one that that is the same that we use for the soil. So according to Rovidis et al. This equation for the stiffness, for the Winkler stiffness at the base for inhomogeneous soil has been published in Brandenberg et al. 2017. Let's talk now about this scaling factor. As I was mentioning, the first scaling factor is accounted for the frequency content. The frequency content, to do so, we are considering this term that is basically considering how much, what's the, how important are the resonant conditions for this system. So it is related to the ratio between the dimensionless frequency and the first mode dimensionless natural frequency for the portion of the soil above the base of the wall. And this is a solution that has been developed by Kuklinas et al. And then there are further modifications to account for soil inhomogeneity that are also presented in the 2012, 2017 and 2020 paper by Brandenberg et al. The scaling factor that accounts for the presence of another structure is also is a formula that has been developed by Brandenberg et al. And there are the same. It's also related to the frequency content of the deposit. And here, this is just to show that there is an actual formula that you can use and you can substitute, and you will have a number for the scaling factor. The last coefficient that scaling factor that we have is the one related to the flexibility of the wall. This scaling factor accounts for the increasing of Ky, so the Winkler stiffness, in case of you have flexible wall due to the mobilization shear stress at the solid wall interface caused by the wall rotation during flexure. To define this coefficient, we did an extensive parametric numerical analysis in which we modeled the soil deposit and the wall, and we applied some, we considered different shear wave velocity profiles because we wanted to investigate also the effect of the inhomogeneous soil deposit. And we apply a quasi-static analysis. So basically, we were pushing the wall, and we were recording all the responses, the pressures. And we were running all this analysis on design safe, and we had a total the combination of all the conditions was produced something like 8,000 different analyses. For each of these analyses, we were able to compute to extract information like this reported here in this figure, and we were computing the stiffness, the Winkler stiffness at the base of the deposit using this expression, in which we were basically monitoring what was the variation of the lateral pressure due to the presence of due to the flexibility of the wall. Again, here there is the difference between the response in the free field condition and the response and the displacement of the wall. The total of this analysis, we were able to, we thought to represent all these analyses and so the flexibility factor related to in terms of beta H, where beta H basically represents the flexibility of the wall with respect to the soil. Beta is represented here and is something that very similar to what we use for piles. And it's able to basically represent, and this is the key of this study, because as we were mentioning before, we are not considering the response of the wall as a standalone response, but we are considering the influence between and the mutual response of the wall compared to the soil. This is, and we were able to do a regression of all these analyses, and this was all more details about the whole procedure are reported in Durante et al. 2018. At this point, let's check how we had the framework, we had the solution, we had all the scaling factor, and we thought about looking for some centrifuge testing to validate our models. The testing, we used the centrifuge testing by Hasman et al. 2016, and basically we chose these because we had, first of all, we had access to all the data. Through personal communication, we were able to have the raw data of all the sensors and the response of the input motion, the ground motion, and everything. So it was easy to apply our procedure. And also we picked these ones because we have, as you can see here, we have different soil conditions and also different configuration, because we had also some configuration where V was equal to 0. So we had also fixed base conditions. So we could verify different boundary conditions that we can account for in our model. Just to, as I was mentioning, we are, everything in our model is, the initial condition we are considering is like inhomogeneous soil profile, and the value of the shear wave velocity has been obtained based on the natural frequency that was that available from centrifuge ambient points before each motion. So we were able, before each motion, to account for the actual soil response. And then we adapt, since we had this centrifuge testing, and you know that basically it's almost impossible to reproduce free field condition if you have a structure in a centrifuge. We use 2D correction to account for no free field condition in the model. So we applied something that was proposed by Brandenberg et al. 2017. For each of that test layout, we had these 5 different motions. And here there are basically all the useful information for the event, and also we reported also the initial properties of the soil, the VH. Something that I was mentioning before is that in all these models, of course, we are using a linear, the soil, it's always linear. It's an elastic, linear elastic model. Somehow we wanted to account for nonlinear effects, and we did what we usually do when we are doing when we have elastic model. So we used equivalent linear model. We were able to measure, we used the procedure suggested by Idris and San, and we were basically analyzing what was the mobilized free field strain level, and we were scaling the actual shear wave velocity used in the linear analysis to account for the degradation of the model of the soil during the different tests. Of course, this is an iterative procedure, and you need more iteration, but it's something that is really handy to do. Once we had the actual shear wave velocity of each test, we were able also to define that beta H, that is basically that is able to represent the stiffness of the soil, of the structure, soil stiffness, soil stiffness. And we found that for all this structure, it was varying from 1.18 to 2.7 roughly. And I want just to remember that BH less 0.5 corresponds to rigid structure. So basically we are not exactly, we are in the flexible structure range. So it's something good, because we wanted also to test how good was our method to account for the flexibility of the wall. I don't have time to go through each test, so I'm just showing you some the general results. And here in this slide, you can see the comparison of the performance of the model. Are plotted the residual, so is the natural log of the measured bending moment minus the predicted bending moment for 3 different plots. The first one is our proposed solution, so the analytical solution. The second one is Mononobio-Kabe, and the third is Sieden-Whitman, that basically is considering 65% of the PGA in the analysis of the seismic air pressure increment. What we can see is, first of all, as I was mentioning, we had few cases for which these are referring to the strongest motion, for which the Mononobio-Kabe solution doesn't provide a value. So because it's infinite, it's reaching the limit. And then we can see that positive mean value indicates under prediction. And this under prediction is approximately by of 26% for the Monod-Okabe procedure and 47% for Seiden-Whitman procedure, while the proposed method is always a much lower error, that is 10%. And as you can read also from the plot, the standard deviations of the residuals are similar for the three models. So there is just a big difference only about the mean values. At this point, in order to make this procedure available to everyone and easy to use to approach, since we, as I said, it's a complex analytical solution, we thought about creating some Jupyter notebooks that implement the analytical procedure for everyone to check, download, play with, and modify as needed. Everything is available and design safe, the cyber infrastructure, and has a DOI, so it's possible to cite and to refer to in if needed. Here, this is just a screenshot of what you will see if you are connecting to the web page. The only thing that I have to mention is that in order to access to these Jupyter notebooks, you need to be registered to the ScienceSafe, but that's a completely free platform, so you can go ahead and just register and then use these tools here. As I was mentioning, you can open, download, or copy the files and modify everything as you need. Also to run some application as an example. I don't have time to go through the specific notebook. I just want to underline that basically you have the notebooks are user friendly. There are all the indication and all the information step by step to be able to successfully run the analysis. I was talking about more different, in order to make these very easy to access and to use for everyone, we created basically some the typical different cases that you can have. So the easiest one is the one that we were referring at first, that is the case of uniform soil with infinite length deposit, rigid cantilever massless wall. So basically is the easiest case that you can have, and then you can add different factors and the more complicated one is that is including all the a lot of features, the inhomogeneous soil with finite length deposit, flexible wood with mass that is constrained by elastic springs at top and bottom. And I want to mention that these springs that you have at top and bottom of the wall are both translational and rotational springs, so you can consider all the combination and all the structural boundary conditions that you like. And this is just a screenshot of the Jupyter notebook. As you can see, as I was saying, here there is all the description, and there is also a help function to have more information for people that want to go in the source code that is also available here in the same folder, and you can play with and modify it. In order to show how this can work, I just want to go through very quickly an example problem. This is something that we take an example, a typical wall that that you can find is a 4-meter wall. Here there are all the information with an inhomogeneous soil deposit, and we consider a site in Los Angeles, and we consider the uniform has a spectrum for a return period of 224.75 years, and we were able to go through the NGA tool to run the UHS and to find the motion that we're able to match the target spectrum, and we were able to find the two motions that are representative of that area for the two return period that we are considering. So as you can see, we have a motion that is with a PGA of 0.28 G, and one with 0.73 G. This information, I'm just underlining this information because, of course, at the end of the exercise, we are also comparing with Mononobio-Cabe results, approaches. In the the only thing that you need to do is to upload in the Jupyter notebook the motion that you want to analyze, and of course put all the information about the geometrical and the stiffness information about your wall, and the code will run in just a few seconds and will give you information about the time series of shear and bending moment at the base and the top of the wall with two different colors. In this case, you have the base in blue and the top in orange. The other plots that are produced are snapshots of soil and wall displacement, subgrade reaction, shear, and the bending moment computed at the time that the peak bending moment occurs. When I mentioned that you can modify all these notebook is because you can also pick the time when you want to be to check your results. So you can pick a different time and just plot everything you want, because the analysis is done for all the. This is just a snapshot of the envelopes. This is the snapshot, but you can also ask for the envelope and everything. You just need to modify a bit the code. And then we did the same also for the other input motion. So this is for 24-75 years return period. And again, here we have the shear and bending moment at base and top of the wall, and then the snapshot for with the variation with depth of displacement, pressure, shear, and bending moment. If we want to compare now the two solutions, just to have an idea of the response, we can see that for the return period of 200 here, the peak of the pressure is about 15 kilopascal. If we compute then the resultant of the seismic increment is about 43 kilonewton. If we compare with the Mononobio-Cabe procedure, we can see that with full PGA, we have 33 kilonewton. And with Sieden-Wittmann method, so using a 65%, only 65% of PGA, we have something like 16. So we have very different value. In this case, looks like that the Mononobio-Cabe is underestimating is providing a lower value for our wall. If we check the results with 75 years, we see that the peak is about 28 kilopascal and the resultant pressure is about 79. In this case, we can check that we can see that the Mononobio-Cabe procedure provided infinite pressure, we can say, while the Sieden-Wittmann 93 kilonewton. So in this case, was the Sieden-Wittmann prevision was larger than the one with our method. That's something that I want, and this is related to the different frequency content. And something that we are considering more or less the same frequency content because we were using these for the motion, but something that I want to show that basically in this case, we had a PGA for the second return period of about 0.7, more than 0.7 G. And so in this case, it was not possible to define a pressure with the Mononobio-Cabe solution. So at this point, if this is what we did until now, what is the future research? So why creating a new project if we already have this solution? Of course, there is always space for improvements, but the main idea of this project is to include somehow the soil nonlinearity, because during our analysis we saw that also when we were confronting with the centrifuge test, including the nonlinearity of the soil in an equivalent linear manner was improving the results, but of course were not perfect. So the idea is to have APC numerical analysis that are able to include at this point through the model of the continuum, the nonlinear soil response, and then using all this information collected in a database and stored, and then will be also made available for everyone. We will do some post-processing data analysis using some artificial intelligence technique. I want just to underline that these techniques will be not like used like a black box, but we'll put physics in it. And all of this is still work in progress. We are just 6 months in the project, and so I will keep you updated, and I will let you know how this goes in the next year or so. So let's draw some conclusions. We saw that seismic pressures on wall results from relative wall free field displacement. This displacement can arise from inertial and kinematic mechanisms. Mononobio-Cabbe procedure and variation capture neither mechanism. The seismic pressure increments has no fundamental relationship to PGA. The proposed procedure resolves conflicting findings in literature and generates an average error of 10% that is much lower than 26% and 46% that was produced by Mononobio-Cabbe in the Whitman, respectively. The procedures are implemented in Jupyter notebooks available on Design Safe, and are easy to use, and that can be downloaded and modified as needed. And finally, ReStructure2.0 is a project funded by the European Commission based at UNICAL that aims to extend the proposed approach, including soil nonlinearity, leveraging artificial intelligence techniques. Here, there are just the main references that I used during this presentation, and I'll be happy to answer any questions. Thank you. It is for later. Okay.
Should we raise our hands, or we can just?
Yeah, you can just ask.
Okay. Okay. First of all, congratulations. Very nice presentation. Very interesting.
Thank you.
Look, I have a question. I have much sympathy, let's say, for these solutions, and I also published a discussion to the paper by Brandenberg et al. 2015, where there is this idea here.
Everything started there.
Sorry?
Everything started there. That was the first paper using,
So I have this sympathy, and Scott and John, when they replied to the, when they made the closure to my discussion, they were, pushing for this kind of approach. Now, my feeling is that this approach is, very much convincing in terms of, physical meaning for, let's say, this layout, this U-shaped layout. But when you go to classical retaining walls, my feeling, but I want to know your idea about that, is that the interaction is more complicated, because I guess that if the active wedge thrust forms, then it's under seismic action. I don't know if you can have the same interaction mechanism, because you have larger pressures than Mononobio-Cabbe, because you used, I guess, the active thrust, not the passive, of course. So you cannot the feeling is that the mechanism is different. So I want to know what do you think about that? If you suggest for classical retaining walls this approach, or if you detect some drawbacks.
So basically, as I was mentioning, this is the first approach, and it was like the scope of this research was the start of that is just to see that there was something that was not working with from the physics based with the Mononobio-Cabbe procedure. Of course, this is not a perfect model yet, because as I was mentioning, also the fact that we are considering we are not considering the static response of the wall, but we are just starting from the dynamics. So you consider only the increment in the dynamic condition. We are going to, in the future, to explore what is happening once there are situations as you were mentioning, and also, but we checked that for freestanding walls, so that is not like a U-shaped wall. We had also in some of the results that I didn't show here, are considering also some shape standard freestanding walls, and the model is performing well also in that condition. And that's because when we are setting the different springs in the new model, you can basically have all the combination. And in the moment when that you change the boundary conditions, you can include some different response of the soil. Of course, in the moment that once you have plasticity and some other response of the wall, we have to see, because we are right now we are just considering elastic response, and everything is elastic. The wall is completely attached to the soil. There is no gap. There is no response, and that is something that also is going to change basically the response. So it's an open question, and we have to check. The important thing is that we wanted to put some physics behind the model, and that's something that you said is like looking at the actual response between soil and soil displacement and wall displacement is helping to have the actual response. But let's see how it goes with more cases.
The feeling is that for freestanding walls, I don't know if mononoble cable can be under conservative. No, I mean, I don't know if you have tried.
The thing is that you cannot say is not in the mononoble cable. It's always related only to PGA, so it's proportional to PGA, and that's it. That's the main limitation.
But my mind is like having a sort of upper bound, because if you are changing the acceleration and it's decreasing, you know, with that, you know. Anyway, we will see.
It's more. We are still working on all these aspects, and the framework was the important part that we wanted to underline. And of course, we are still working on that, and there is a lot to do still. That's why we are here.
Another quick question, because now I was thinking. I'm wondering, in reality, in this kind of L-shaped walls here, as they are, I think, quite strong. I mean, if I consider the normal heights and widths and so on, I'm wondering if, despite this solution can give results that are, in terms of pressure, of course, higher than mononoble cable, which is the absolute value compared to the strength, let's say. I mean, did you try also to understand this? Because if you, let's say, if you're mobilizing a truss that is 5% of what the wall can sustain, and mononoble cable 3%, I understand that mononoble cable is underestimated, but maybe in this kind of walls, you have, I mean, real, you know, over strength compared to what you are able to mobilize, with the fact that if you have low frequency, of course, there is almost zero. So I understand all the problem, of course, but I don't know, did you try to apply to real geometries, real cases to check with minimum reinforcement, for example, if you're still far from the strength?
Not yet, because we are not using we don't have we didn't use these yet. We were using only this.
Sufficiently clear. My only concern is that maybe, you have a big error, maybe, but for this kind of walls, they are so strong in general.
The point is not most of the time for this approach is not related to the fact that it's not common to see also during strong earthquake retaining walls collapsing. So it's not something that we are doing to increase, because usually we don't see, it's very rare to find retaining walls that are collapsing after a shaking. The point is more that maybe most of the time we are over designing them. So maybe the idea is also to,
Because maybe with the minimum, maybe you will find out that with the minimum reinforcement prescribed by codes, you are already far from what you can mobilize in terms of traffic.
Yeah, that's something that we were exploring. That's the point of checking if it was overestimating or underestimating is something that is. Can you hear me? Yeah, that is just related to that. That maybe you don't need to have these so strong walls. Maybe you can just have smaller work and you can save materials and everything. Hello?
Hey,
Okay.
Margot, how you doing?
Hi. Good.
So, great presentation. I wanted to ask about the inclusion of nonlinearity. So, currently, you said that you guys assumed that the soil was linear at the base.
Yeah.
What ways?
Yeah. All the.
So what ways? What in what way? How would you account for? Because I'm assuming because you're providing an analytical solution in some sense or a numerical solution.
So we are during my project, I'm planning to run a numerical analysis, of course. That's
Okay.
the way to include. So I will create some bunch of 2D numerical models with different soil condition, wall boundary conditions, and so on. And then we will try to adapt this procedure to using machine learning to include somehow the results from this study, this numerical analysis, to modify the current version of the model. So basically, we will use numerical analysis.
So is it that it's impossible to include soil nonlinearity in an analytical solution?
It's really hard. Already with that solution, we were not able to have a closed form solution. We used already numerical approximation to provide solution. Adding soil nonlinearity is basically it's not doable.
Okay, that makes
not
sense.
Directly, at least. So the best thing is just to use like numerical analysis where you can use the soil models that you want and just go with that.
That makes sense. Okay, that makes sense. Awesome. Thank you.
Thank you. It's 6 o'clock. So please, if you have any additional question, please contact me, send me an email, and I'll be happy to discuss with you. The only thing that I want to do before ending the meeting, I just want to tell you what's coming next. And the next webinar will be on March 17. And we are still defining the time. Will be more or less at the same time as today. But the speaker will be Professor Scott Brandenberg from University of California, Los Angeles. To be informed about that, you can. Most of you already subscribed for the newsletter, but you will find more details very soon at the event webpage of the website. So that said, thank you everyone for coming.
Sorry, do we know already the topic Scott will deal with?
Will be on soil structural still on soil structural interaction problems, and we are but I don't have the title yet. Okay, but we will let you know soon. Will be on soil structural interaction. Okay, so thank you everyone for coming. It was great. And I will put the registration on the web page, and I hope to see you next time. Thank you. Bye bye.
Thank you.